now. Welcome to Foundations of Programming Day 17. We're going to pick up from where we left off yesterday. We covered big O notation and we started common problem solving patterns. Uh, the first one we were talking about was like frequency counters. We did one example, which was specifically the frequency counters of pi. And that's where we left off yesterday. And we didn't start anagrams because I didn't want to start something and not be able to cover it in depth. So we're going to start today off with this specific problem, which is going to be anagrams.py. So y'all should be able to open up your VS Code. And it should be lesson 12. You guys did frequency counter yesterday. Today we're doing anagrams.py. Empty pi file. The actual exercise will be in the README. So given two strings, right? Up to this point, you guys should have an idea of what an anagram is. You've probably seen it here or there. But essentially, an anagram is a word that when the letters are backwards, right, written backwards, it spells the same thing, right? So right function determines the second string is the anagram of the first, right? An anagram is a word, phrase, or name formed by rearranging the letters. Oh, I'm dumb. Never mind. I'm thinking about a palindrome. An anagram is taking the same letters in a word and creating a different word or phrase with the same amount of letters, right? I guess what's a good example? I mean, we could the word anagram, I guess, itself is an anagram. But I wouldn't really call this an actual anagram. I mean, I guess it would be considered an anagram, but it's not an actual word. What's a good example?
One in the README is Cinema and Iceman.
Cinema is a really good one. Yeah, I think that's a good one. Cinema and Iceman. That's a perfect example. I should have finished reading the dang README. That's why I'm getting ahead of myself. But yeah, thank you for that, Michael. Get me back on track. Yeah, Cinema and Iceman is a really good example. Um, Technically, you would count these as anagrams, but I mean, realistically, these nagram isn't really a word itself. Same thing with AAZ and ZZA. I wouldn't call these. Well, first and foremost, it's not the same, but still, you know what I'm trying to get at. These two are not even the words, but it's being considered as a valid anagram. Well, long story short, right, this function should be able to take in two different strings and it's going to determine if it's an anagram or not, right? So it should just return to you true or false. Uh, so if you're thinking about this, logically speaking, how would you determine if string A is an anagram to string B? If you had to break this and dissect it into smaller problems, what would you want to do? I don't expect a full on answer. Just kind of like start me off, somebody, and then we can just kind of piggyback off of each other's.
They need to have the same number of letters.
Right. So they probably we want to make sure they're the same length, right? They have to have the same amount of letters, even if they don't have the same frequency of letters. The first check that will automatically probably eliminate any or a certain amount of possibilities is if the words themselves aren't even the same length, then chances are they're not gonna be anagrams as it is. So yes, that's a very good one, Nick. That's what we call an edge case, right? Where it's not going to apply to every single possibility, but there is the chance that we might encounter input where they don't share the same length. We have different amounts of characters in each string. So yeah, so we might want to check, is the length of string A the same as string B? Right? That's going to be one thing that we're going to want to check for. So thanks. That's a good one, Nick. Someone else. What else what we might want to do, or how will we start this off, or how we approach this problem?
Maybe you have to have the same amount of like particular characters or variables, like in terms of like the same combination, like as in like if a piece is missing, like so for example, AAZ, if it was a Z was missing, then maybe it wouldn't have enough to
Right.
be able to do it.
Right. So Daniel Bender here, it's kind of going back to like the frequency counter, right? So just like Daniel Bender said, so although we're the same length, we also have to make sure the same frequency of letters appear on both sides, right? So if the Z appears once on string A, the string has to appear once in string B, right? They should have the same frequency. So uh, it's just another version of frequency counter here, right? It's the problem using the anagrams, but this is another example of how you could use this specific strategy of using a dictionary to keep track of the frequency of the appearances of certain characters, right? Which is why this problem is still within the same subject as frequency counter, right? So we're still going to want to be able to identify how often does the Z appear or the A or any specific character. If it appears once or twice in one side, it better appear the same amount of times on the other side, right? So we're gonna want to keep track of this. And to piggyback off from what Daniel said, we want to accomplish this task, we're probably gonna want to iterate through these strings because these are sequences of characters. So we're gonna have to go through each single character and then compare it to the opposite character as well. And then we might want to create some kind of data structure that we can use to keep track of what the appearance of a character is throughout the entire iteration, right? So this is the way that we are going to want to approach this. So with that explanation taken care of, let's go ahead and give it an honest try. So time is 5:41. We're going to try this till 6. Then at 6, we'll come back. Hopefully we can have a volunteer. If no one finishes, then I'll take it from there and we'll go over the solution. But let's go ahead and come back at 6 p.m. I'll see you guys in a bit.
Here,
This meeting is being recorded.
you can see my screen, yeah?
Yes, sir.
Can you see my code?
Yes, I forgot your VS Code. Do you have it like to be transparent or like opaque?
Oh, so no, this just not to get too sidetracked. So this is NeoVim. So I'm on Hyperland NixOS. So I'm doing everything out the terminal actually.
Ah, okay.
Yeah. So this is NeoVim, and but yeah, I can just open up my terminal down here too as well, which is pretty nice, I think.
Yeah, that's
Um,
awesome. Okay, okay. I was just curious. I was like, why can't I see through your screen? That's so weird. All right.
yeah. So yeah, so I was doing valid. Well, we're doing this one right here. So I did another edge case. I wanted to check and make sure the strings are actually like lowercase, so that way there isn't like a set uppercase one that's in one of them or something like that. So that was just a random edge case. I still left them as string one, string two, but it just makes them lowercase if that makes any sense. And did like we said before, the length, checking if the length is not equal to string two, it will just return false and just leaves the entire function. As we get down here though, so I did it, so the way I did it, I decided to count the characters by putting them as like key value pairs in a dictionary. So I have this dictionary here called character count, and it has for every character that's in string one, if the character is in like the character count, which means it's like already like listed as a key value pair in here, then we'll just increment it as one. But if it's not, then we'll just go ahead and start it as a key value pair and just initialize it to one basically.
Right.
So I did that. I also did print. There's a print statement here. Only reason why I have this here is just to make sure like I'm like actually have the key value pairs that I'm looking at in character count. And then as I got down here for another loop, I did another loop. I did for character in string two, and this is just checking the second string. And if I was basically saying if the character is not in the character count, which means it's checking if that character is listed as a key, like not it's not looking at the value, but just looking at it's like looking at the key. If it's not in there, it just immediately returns false. So I'll just go out. So if that's not inside my character count up here in this dictionary, then it just returns false and exit it. Otherwise, I did it where I subtracted, like I decrement like the character count by one. But if it goes down here, if character count is less than zero, it'll just return false. Like so, if I get like -1, then I'll just go ahead and return false. But I'll just loop through string two and just check and like just decrement it all. And if it ends up decrementing it all, then I just return true. It's kind of a very funky function, but it actually does work. So if I go here, then I just go ahead and just run Python 3 anagrams pi. It just each one. The very first statement is checking the length, so that's why you're getting a false right here. And then the second statement is returning false because of it's not matching up to ZZA in the second string. So that means that this one is an anagram. The third one, anagram, returns true, so it does say it's an anagram. Car returns false, rat car. And then the last one is QWERTY, and that one returns true.
I don't
And
know
that's
why I feel like there's something that can go wrong there. I don't know if I'm losing my touch or what. If char is less than zero, return false.
yeah. So basically, what was happening was if this one right here, like sometimes, like if it'll just keep decrementing and just won't like,
Right.
it'll just
That
like
and
negative.
it'll keep decrementing it if
Yeah.
it exists in
Right.
char. It also exists in string one, right? So if it exists in both string one and string two, right?
Yeah. They
But
kind of. Oh,
if
go
there's
ahead.
an if there is another, hmm, I
I was
want you
going.
to do on line 10. I want you to switch Niagara, that second argument, switch it
Yeah.
all to A's.
Oh, this one right. The second argument switches
No,
all
the
the.
second one. The second one. Yeah,
Oh,
that
sorry.
one. All A's. I'm sorry. Maybe yeah, that one right there, all A's. So
One,
one,
two.
two, three, four, five, six, seven, seven.
Yeah. One, two, three, four, five, six, seven. Okay. So now let's go ahead and
I mean,
oh,
I guess that would work.
hold on. Let's go ahead and try it. So that one should evaluate a fault or
It should,
true
yeah, it should
statement.
be like to false,
So this right here. So this is the one.
false, false, true. What am I thinking? Hmm.
I could just hold on. Let me make sure. Like since we're focusing on that one, I'm just gonna comment these out really quick, and then just uncomment this one, so that way we can actually have
Let's
it.
remove all the A's. I guess that's not where my thought process is. I'm trying to visualize what I'm thinking here.
Okay. Yeah.
Let's remove the second argument of all A's. Let's type in,
Okay.
put it back to where it was. Yeah, like just put type in anagram. But this time, instead of the two A's, take
Mm-hmm.
one A out and put a K.
Okay. So there's three A's. You want me to just take out the?
Yeah, just either one is fine, and just put a
Okay.
K instead.
Okay. So go back
Which,
here.
which actually it should be fine. No, okay, I see why this is working. Okay. Okay.
Wait,
There
what
we go.
happened?
Yeah, I see why it's working now.
Oh.
It was just I was struggling to visualize what the heck was going on here. But if it doesn't have the proper count, hmm, what if we do? Okay, no, it's good. That's really good. That's a really good solution. It took me a while to really understand your code, but that's good, man. Awesome.
Oh. Thank you. Thank you. Yeah. This one was kind of. This
I'm
part was
telling you guys,
honestly it was this part that was kind of like breaking my brain a little bit. I was like,
it
why?
was breaking my brain right now.
Yeah.
Wait, I have a question. What happens if the count is greater than zero?
If the count is greater than zero,
Like if the second string you're checking has more letters,
has more.
or trying to think.
It won't get there because we on line 27 we
Oh
checked that
yeah, there.
already.
All right, yeah, it works. All right.
Yeah, it's good. Yeah,
Yeah.
I was trying to see. 'Cause I feel like it should have not worked. Then as we started working through it, and it showed me the examples. I can see why it works. That's good.
Yeah, and that's this part just kind of like messed with my brain a little bit. I was like, wait a minute, I have to decrement it and make sure it gets to like zero, but it can't be less than zero because if it gets less than zero, then that's when it like says no, it's not an
Yeah.
anagram. Yeah. But okay, it's yeah, but that's the one.
Good stuff. Good stuff. All right. Thank you for that example, Kevin. That was a very good solution. Um, I tell you guys, man, sometimes it takes me a little bit longer than most people, so I have to kind of really see it and just kind of visualize what's happening, and that's okay. If for whatever reason you guys are in the same boat as me, then ask your questions. Ask to see it in a different way. Try to see different solutions, and really understand why stuff is working and why it's not working. That's the only way you're really gonna learn. For me, I have to see it multiple times to really understand what's happening. But that's gonna cover the frequency counter, right? So being able to use a dictionary to keep track of certain occurrences. And really the big thing here about the dictionary that we're taking advantage is uh, the ability to be able to access elements in a dictionary using key value pairs, right? Whereas in the list, unless you have the index specifically what you're looking for, it increases your time complexity. So the dictionary is a very powerful data structure that allows you to access data without increasing the time complexity, so still having good performance in your code, right? That's really the thing to take away from this, right? Easiest way to increase your time complexity is probably change what type of data structure you're using. Well, it's typically the first way to go, right? If you're using a list, chances are there might be a better way of doing this with a dictionary, and that will automatically typically increase your time complexity significantly. All right. The next problem that we're going to talk about is going to be multiple pointers patterns, right? So this pattern, and you're going to notice that the name really kind of gives it away what these patterns are really doing. This pattern consists of creating pointers. Now, when we say pointers, that's really just a fancy word of a variable, right? We're creating temporary variables to specify certain points in our iteration that we can compare to each other, right? So this pattern consists of creating pointers that correspond to an index and move towards the beginning and or middle of the string slash list based on a certain condition, right? It's very efficient for solving problems with minimal space complexity. Let's see. I'm not quite sure exactly what this picture is actually doing, what they're looking for, but here's a very prime example. They have two pointers, right? One starts at the beginning and one starts at the end, right? So when instantiating or setting these pointers in values, you essentially create two variables, right? P1 and P2, right? It could be pointer one and pointer two, or you can name it start and end, whatever you want to call it, right? Start, if you want to grab the beginning of your iteration, what would you set that pointer to? Not your question.
List bracket 0.
List bracket 0 or just set it to 0, right? You can use that variable as the index itself, right? So yes, you're on the right track, Kevin, right? If you want to start a pointer at the beginning of your list, you would set it to 0. That way, when you go to access different parts of your lists, you use the start and the end variables as the index that you want to check at, right? And then same thing for the pointer at the end. How would you grab this last pointer? How would you set a pointer at the very end of your iterable?
-1.
The length of the list.
I would
-1.
argue, yeah, length of the list
-1.
-1 would be a little bit more accurate, Michael. Would that work? Sure. But typically you want to be very specific of what you're working with, right? So you don't know, how do I say this? Yes, you can use -1, but the reason why you want to specify something like getting the length of the list and then subtracting one to get a very specific number is because typically you're going to be manipulating these pointers, right? You're going to be subtracting from them or adding to them to shift them left or right. So it'll make it easier to work with if you have the actual index of what you're trying to grab, right? For example, this is 1, 2, 3, 4, 5, 6, 7, 8. There's 8 items in here. So if I would have used the length method on this, it would return 8 for me. What index is the 8th item here? Index 7, right? So if I want to grab index 7, I would grab the length of the list, which is 8, subtract 1. It'll give me the index of the last item. right? And now I know that my end pointer is the number 7. And if I want to shift it to the left, I can subtract from the 7 and it'll move down to the left, right? When we do stuff like -1, if that variable set to -1, now you have to work with the negatives. It can get very confusing. So it's easier to just grab the actual index that you're looking for, which is the length of the list, -1 to grab the last item. Student multiple pointers. So let's look at this example. It kind of throws you right into the deep end of the pool with some of these examples. So I do apologize for this one. But let's look at it. Don't look at the actual code snippet on the slides. Let's just look at this real quick. Right, we're going to write a function called same, which accepts 2 lists. The function to return true if every value in the first list has its corresponding value squared in the second list. The frequency of values must be the same. Oh, this is wrong. I'm using the wrong one. This is frequency counter. I should have known the moment I started reading it. Multiple pointers. There we go. Here we go. Write a function called sum0, which accepts a sorted list of integers, right? Sorted list of integers. So you know it's a numeric order from left to greatest, right? From least to greatest. The function should find the first pair where the sum is 0. And it's going to return a list that includes both values that sum to 0 or -1 if a pair does not exist. So let's copy this, and I'm going to show you this in a drawing to really understand how the multiple pointer works. CO Draw is working with me pretty well today, which is good. Yesterday, I don't know what it was doing, it hated me. But let's take the first one for example, right? Here is, I spoke way too soon. No. Okay, we're gonna say list 1 is equal to -3, -2, -1, 0, 1, 2, 3. Right, this is my list right here. Right? So the problem wanted me to write a function that finds the first pair where the sum is 0, right? Return a list that includes both values that sum to 0 or -1 if a pair does not exist. So the first example returned -3 and 3, right? So in this example here, the combination of 2 numbers when added together that gives me 0 is the item here and the item at the very end of the list, right? -3 plus 3, that's positive, will give me 0. So essentially what we have to do is we have to go through every possible combination we have in here to figure out when added together, does it equal 0 for me? So the picture that I showed you guys initially is a little misleading because the example we show you starts at the end. It does not necessarily have to start at the end. Multiple pointers doesn't necessarily have like a strict start. You don't have to go from start and end. You can start both of them at the very beginning, and that's okay. Right? So essentially what you should be doing is you should have P1, which is going to be pointer 1, will be 0. What are you doing, bro? Uh, why? Why? My therapist told me to practice patience. All right. My keyboard, there you go. I'm going to erase you. So P2 is equal to 1. So here's my 2 pointers. I got pointer 1 and pointer 2. Right? Pointer 1, because it's set to 0, when I do list one at index P1, it's going to grab the very first item, and P2 is starting at index 1, right? So it's going to be -3 and -2. So essentially, what I will do is list 1 at index P1. This is going to end up giving me -3, right? List 1 at P2 is going to give me -2. That's how we're working with the pointers, right? The pointers allow us to mess around with the indexes that we're working with. So when you first start this, the way that you're going to use your pointers is to point to a very specific point in your list. And you do this for a specific reason. If you didn't have pointers, what's a different approach that you might have naturally taken to try to check every possible combination?
Nested for loops.
A nested for loop, right? So Nick hit it on the head. If we didn't take a pointer approach, your natural approach that you would have probably resorted to was going to be a nested for loop. This doesn't require a nested for loop, right? What we're going to do is we are going to check every possible combination from start to end only through one for loop, right? And how do we do that? Well, we're going to start a for loop that's going to iterate through every single number here, right? The first time it iterates, P1 is going to start at 0, and P1 is not going to increase until we check every possible combination that P1 can have with every other number. So when we first start this first iteration, P1 is going to check the combination with P2. We're going to see, hey, does list 1 at index P1, which is -3, plus list 1 at index P2, which is -2. When added together, does it give me 0? If it doesn't, cool, then this is not a good combination. So I'm going to go ahead and I'm going to increase my P2 by 1. So now P2 will equal -1. And then I'll check this combination. -3 plus -1. Is that 0? No. I'm going to go to 0, and then 1, and then 2, and then 3. Now, because this scenario, it catches it in the very first try, we won't have to do another iteration. But let's say hypothetically, if the answer wasn't here, right? Once we do the first iteration, the next time this for loop runs, we're going to increase P1 by 1. And now we reset P2 to the beginning of wherever P1 is at. So we'll take with the current position of P1 and we'll increase it by 1. So now we check -2 plus -1, -2 plus 0, -2 plus 1, so on and so forth. And until we find it, we're going to keep shifting our pointers to the right and checking every possible combination until P1 is equal to the last index. Right? Do you guys see how this works? So without using a nested for loop, I can run one for loop that's going to go from start to finish. It keeps the time complexity at O of n, and I'm still able to check multiple different combinations using these 2 pointers, right? Where if I didn't use the 2 pointers, what would probably end up happening would be something like for A in list 1, and then I would say for B in list 1, if A plus B is equal to 0, return A comma B, else continue, right? And then this will run and check every possible combination between these. So using a pointer, I'm able to avoid using a nested for loop like I'm doing here. That way, if I just keep it this way, all I have to do is for num in list 1, or honestly, it could be for I in range of the length of list 1. If list 1 P1 plus list 1 P2 is equal to 0, then we can return P1, P2, right? And then if it's not equal to 0, what do? We increase P2 by 1 and so on and so forth. We go ahead and write this algorithm here. So we can have a nested for loop approach, or we can have an O of N approach, only using one for loop and leveraging the fact that we can use pointers to avoid this monstrosity right here. Right, because this right here will give you a time complexity of O of N squared, while doing pointers will keep your time complexity at O of N, therefore being more efficient, right? So this is a really good algorithm to avoid nested for loops, but still be able to check multiple combinations like this. And with that explanation, I'm going to hand it over to you guys. So I'm going to pause the recording.
So originally I was going to pass in J. Let me delete that out of it because that's no longer needed. Because I was going to use it as a counter, but then I just set up a counter system. So I set my counter to equal to 0, so that way I can always have that one designated pointer to slowly go through each one, because we're comparing one of these values with another value. So initially counter is set to 0, which would be -3. And then I did a while loop. While counter is less than the length of the list, it should be less than or equal to make it actually true.
I'm gonna stop you right here, Daniel. What do you guys see here? What is line 4 and line 5 doing?
Space
I want you.
complexity n squared.
Yes,
Time complexity n squared. My bad.
time complexity is O of N squared, right? A while loop and a for I in range. This here, it's tough
But
to
I
say
did look it
actually.
up
So
because it said a while loop using a counter is just big O of 1.
that's what I was about to say. It's a little, it's a gray area
because it's just comparing two things.
Right, and counter, because he has this condition, it does have a stopping point, but to be fair, counter is gonna keep going, and really, the while loop is gonna increase in complexity dependent on the size of list. So actually,
Yeah, what if the list was a million items long and
right,
it went from negative, I don't know, the last two numbers were the answer. Like literally the last two of the list, right? That would still have to iterate through almost everything.
yes, and that type complexity, that in theory, right, with what we know as ready for what we've been talking about, that is going to be old N immediately, right? Because counter is going to keep going. It's going to grow linearly to the size of whatever list is. So if counter has to keep increasing until it iterates through all of lists, then if list is 10, it's going to iterate 10 times. If it's a million, it's going to iterate a million times. So therefore, this while loop here is O of N, right? And then once again, you do it for I in range. This for I in range is in the range of whatever the list is as well, even if you're subtracting the counter.
But yeah, I was going to say, I was like, even if it was a million items, right? So like it would kind of offset, because the second part right here, as the counter is counting up, it's also subtracting for that second loop. So it basically is canceling itself out, as one is raising in value, the other one is decreasing in value. So the time would always be that just one constant of that one for loop.
Right.
Because you're taking away data as you're going, you're removing that data from that list. Because
okay, I see.
once we loop over -3, we'll never visit that -3 again, because we already know that once we go through this entire list, that if you know what I mean.
Good point.
If it didn't equal 0, then it'll just move on to -2, and it'll never see that -3 ever again.
True, and that's a very, very valid point. And I think Daniel's correct here. Although yes, counter does grow linearly with list, the fact that the for iron range is it's actually going to be less every single time because we're subtracting counter actually counteracts that Olivin squared, bringing it back to Olivin. So that's actually very smart. Um, yeah, I can't argue with that logic, Daniel. This is Olivin. Good stuff. Okay, continue. Good conversation
The
though. That was
one,
actually a good point.
mhm. The one case that I had to always look for was if the counter and the list are equal to zero. Because where it was happening was is this one right here. So list counter would come over here and it would see this one, and for whatever reason, my list, even plus the counter down here, was also seeing that same exact zero. And it was only happening in that one test case. I don't know why it was, but like when it was exactly 4 digits long, it was always seeing that. So then I had to basically hard code that in there to bypass that one single test case because it's always going to be a consecutive list of numbers. And then basically as it goes through, my one pointer right here would go through every single one. So -3 would then be compared to -2, -1, 0, 1, 2, and 3. And if the test condition ever resulted in a 0, it would return us that pair. If not, then it would just add 1 to the counter, and then it would loop back through. And then it would swap to -2, and it would compare -2 to -1 to 0 to 1 to 2 to 3, and just kept doing that.
Yeah, yeah, absolutely. Well, this is
Then,
a little different than how it was intended to be done, but they're still using pointers. It's still old and so I give this an A plus. Good stuff, Daniel. Right on. Okay, it's working too. Okay, cool. Good job. Thank you, Daniel, for the explanation. Really appreciate it. That was a very good explanation and demonstration. It gave us a talking point. We were able to see how differences between these two, and that was cool. Awesome. Thank you for that.
I do want to
Okay.
see Nick's though, see how he did it,
Yes.
because I'm kind of curious the other ways to do it.
Sure. Nick, would you mind sharing yours and demonstrating your answer?
Yes. No, I do not mind. I did mine the exact same way, and then I stared at it for a while and realized that it was O of n squared. Can you all see my screen?
Yes.
Mhm.
Okay, so here's my original answer, right here in the commented out section. Mine is, I guess, a less sophisticated version of the one we just saw. So there's a counter. Uh, while the counter is not the end of the list of ints, it goes through and it skips has a hard count or a hard case to skip the when the counter is the same. Because I was having the same issue as you,
Mhm.
where in test case 2 or 3, the 0 would compare to itself and pass. So I had to add this if statement right here. If the I and the counter, or the current index and the counter are the same, you just continue the for loop because you're comparing to yourself. Don't do that.
Mhm.
Um, and then so and then the condition was if the list of ints counter plus e is equal to 0, return that. And if it gets through all that and none of that's true, then it increments the counter by 1 and keeps going. However, when I was looking at that, I was like, oh yeah, that's O of n squared because I got a while loop with a for loop inside of it. So I was like, okay, I got to find a better way. And so I was sitting there and I Googled, I cheated a little bit, and they said that you should use multiple pointers like this from the start and the end. And so like, oh, okay, I'll make a start and an end index, and I'll just work my way in from there. And so how I did that was as long as the start and the start is less than the end, and this requires it to be an ordered list, otherwise this won't work. Um, the sum is the two values added together. If the sum is 0, then we've got our condition and return that. I forget if it wanted a list. Yeah, it wanted a list of the two values. Else, if the sum is less than 0, you need to move the start over to the right by 1 because you've got too much of a negative number and you want to go more positive. Else, technically it'd be another elif if the sum is greater than 0, but it's already taken care of. You need to move the end the right-hand index to the left one because your number is too positive. And you keep running that back and forth until they either meet this condition or you return a -1 because no match was found.
Awesome. Good stuff, Nick. Yeah, a little different than what Dino is, and I think it closely matches the solution that we have on the slide closely. Good stuff. Go ahead and stop sharing your screen, Nick. Thank you for your demonstration. Both good solutions, guys. Good job. It's cool to see you guys go from like guided application to like now, or from when you first started coding, seeing you guys come up with solutions, which is awesome to see every single time. Let's go ahead and go to our slideshow. So here we have the not so great solution of how they approach this problem. And the not so great solution, which is what normally somebody that hasn't encountered the algorithm of using multiple pointers, they would naturally try to do a nested for loop, right? Or they start a for I in a range, they go through the entire list itself, and they start a nested for loop where they're grabbing the start of the initial for loop, but they increase it by 1, and they're using that to compare each other to see if they're equal to 0, and then returning that list item. If not, if at no point does any of these combinations equal to 0, then we return -1. So that was our not so great solution. The point just allowed us to come up with a method that kept us from increasing our time complexity from O n squared and reduced it to O of n. Right. So here is a much better solution using the pointers. Noting that we have left and right here. The left starts at index 0, and the right, they grab the length of the entire list and subtract 1 to be able to grab the very last item in this list. And they do something very similar that Nick did. While left is less than right, we are going to run this iteration. So left starts at 0 and right starts at the very end. So right off the beginning of the first iteration, they're comparing the sums of both of these before we even move any of these to make sure that they don't equal to 0. If it does equal to 0, then we just right off the bat return what the two numbers we have, which would be the first index and the last index, right? If it's not equal to 0, then in that case, we're going to shift either right or left depending on what the total is, right? So because this was a sorted list, if the sum of both of these numbers was greater than 0, that means the item on the right index is too high. We need to make sure that we lower the value of that number by shifting to the left. If the total was too low, then we shifted we shift the left to the right and vice versa, right? So that's kind of what we do here. If total is greater than 0, that means we need to bring the right to the left side a little bit because obviously the sum is too great. That means the right number is too high of a number that when added together, it's going above what 0 should be. So we subtract it. But if total is less than 0, that means the addition of both numbers isn't even equal to 0. It's less than that. Then that means left needs to be increased, right? So this takes advantage of the fact that it is a sorted list of integers to come up with a solution. And if at any point we don't encounter 0 by the end of the while loop, then we just return -1, right? So we see here 3 different ways of how to approach this method, but both ways use some kind of method to keep track of what index we're working on, and then using that variable to compare it against other variables just by some simple math like +1 or so on and so forth. We're going to skip unique values. If you feel like you need a little bit more work with multiple pointers, then I challenge you to take up the unique values challenge. Try this one out on your own. It's going to be a similar concept to the one that we just did. So if you feel like maybe you don't understand multiple pointers just yet, try this one out. Multiple pointers is one of my favorite algorithms. I use it a lot. Make sure you actually add this to your tool belt and remember that this is one of those problem-solving patterns that you can, kind of bring up whenever you encounter a solution like this. It'll increase your time complexity. The next pattern that we're going to talk about is the sliding window. All right, so this pattern involves creating a window, which can either be a list or a number from one position to another. In short, right, the term sliding window, or just really window in general, really is just a fancy word of saying a sub list, right? We create some kind of sub list that is a smaller version of our overall list, and we're comparing the values within a specific range of indexes, right? Um, we use this quote unquote window or essentially the sublist to check if we meet a certain condition. Depending on the certain condition, the window will either increase or it's going to close, right? So by increase, we either shift the right edge of our window to the right, therefore taking in another number within our sublist, uh, or we might either decrease the window by subtracting one of these, removing one of these indices from our sublists to take a smaller range of numbers. Right, so it's very used for keeping track of a subset of data in the list. Really, just another name for a sublist, right? And I want to harp on that keyword I just used, the sublist, right? A window, subset of data. These terms are used interchangeably whenever you're looking at some of these problems. The biggest issue really when tackling some of these data algorithms, structure problems that you might encounter in interviews is trying to figure out what the question is asking from you. And the most common question I get asked, like, "Hey Roger, like I understand these methods that you're teaching us. Like I understand study window, multiple pointers, but then I read the problem and I don't know how to even gauge which algorithm should I use." And really, what it comes down to is being able to use context clues. If you guys remember that from elementary school, being able to read the problem and take keywords from the problem that give you a clue, like, oh, this is gonna be a multiple pointer problem. I'm gonna require multiple pointers to keep track of where I'm working in my iteration to figure out a combination of such sort, right? So certain keywords are really gonna be what's gonna clue you in to what method you should take to approach a problem. Let's look at the sliding window example so we can get a better view of what it's referring to. All right, so we're going to write a function called max sublist, right? Here's the term again, sublist, sum, right? Max sublist sum, which accepts a list of positive integers and a number called num. Right, so we're taking two arguments, right? The first argument this function is taking is a list, and the second argument is num. The function should calculate the maximum sum of n consecutive elements in the list. That n consecutive is that num that's being passed in. Right, so it's a little misleading. Maybe I should put here a number called num, and then maybe put here like n to specify that num is actually the n consecutive elements. So in short, what this is saying is within the sublist, you're going to find a quantity of numbers that are equal to the num that are being passed in. For the example, the first one, we're getting 2 as num. So within this list, we have to find two numbers that are consecutive, meaning they're back to back, that when added together gives us the max sum combination of everything in here. All right, so here on the first test case, it's passing in 2 as num. So somewhere in this list, there's two numbers that are back to back that when added together is going to give us the max sum. And we can see it here, 2 plus 1 is 3, right? That's the first combination. The next two consecutive numbers is 2 and 5. When added together, that's 7. So obviously right here, this combination of numbers is already greater than this combination of numbers. So this combination of numbers is definitely not going to be our answer. This one's already looking like a good choice because 5 plus 2 is going to give us 7. The next combination, once we shift the window to the right, it's once again 5 and 2, giving us 7. So we have two combinations right here, index 1 and 2, and index 2 and 3. Both of them, when added together, gives us a maximum of 7. Let's continue. As we slide our sliding window to the right, we now have 2 and 8. These added together give us 10. So these two right here, these two consecutive numbers, give us a much higher sum compared to every previous combination that we've encountered. So we're going to annotate this. We're going to write it somewhere in some kind of variable. But we're going to continue with our algorithm. We're going to check the next one, 8 and 1. That gives us 9. That's not good. We shift our window to the right. We have 1 and 5. That's 6. So obviously, the highest sum that we encountered was the combination of 2 and 8, which is 10, right? So the max sum of n consecutive numbers, which is 2, is going to be 10, right? Because this combination of two numbers of 2 and 8 gave us 10. So the answer ends up being 10. Let's check the next example. The next example, num is going to be 4. So we need to find a sublist of 4 consecutive numbers within this list that when added together gives us the max sum. So we're going to start our window right here with the first 4 numbers. We have 1 plus 2 is 3, plus 5 is 8, plus 2 is 10. So this combination of 4 numbers gives us 10. When we shift our window to the right, this gives us a different combination. This gives us 17. 8 plus 2 is 10, plus 5 is 15, plus 2 is 17. So this is a much higher combination. So right now, my max sum is 17. When I shift it to the right, this gives me 16. When I shift it to the right, this gives me 16. Right? So the max sum that I encountered was 17, which is why the answer is 17. Right? So we are essentially creating a sublist, right? A quote unquote window of a range of numbers. That range of numbers is going to be dictated by the num being passed in as an argument. And we're going to move that sliding window all the way through our entire list. And every single time that we move this window, we're grabbing the max sum of the combination of these numbers to see if we've encountered a new max sum. And we're keeping track of this, right? Does everybody know how this works? Does anybody have any questions? Do you want me to write it out or draw it out? Okay, let's take let's go into 7:35 and then we'll come back at 7:35 and give this a go. You're good to go.
Okay. It was sliding window, right?
Correct.
So function gets passed a list of integers and a number, and you're supposed to use that number to develop a window to look over the list and find the highest sum that's within that window. So started off because that one test case, the list was smaller than the number, I just returned none. Else, or I guess if that doesn't happen, I make a start and I make an end of my window indexes. So my start is always 0 at the beginning of the list, and my next index, the window end, is the num that's passed in. I create a variable to store the rolling sum, and I did a while loop. So while the window end is less than the length of the list, because obviously you don't want to go outside the index, otherwise you're going to have problems. I do a sum, which is the sum of the list from the window start to the window end. If statement, if the sum is greater than return sum, then I reassign the sum to return sum. So that keeps track of if it's higher than the previous sum that was recorded, it keeps track of it in that variable. Then I increment window start and window end. So the whole window shifts over one unit, loops through that while loop. At the end, it returns sum. And so if I run it, I came up with the same answers that they did. And I did a couple extra test cases just to make sure that what I did was working. So 10, 17, 6, 13, none, none, and 9 per my test cases.
Awesome. Yeah, right on, man. Good stuff. Yo, Nick's killing it, man. Nick's y'all's competition.
I like seeing Nick's stuff because like he has the fancy syntax and like I have to do like all of this old school brute force stuff because I don't know all the syntax.
Well,
So it's
see,
always good to see Nick's.
well, that's funny because I think the same thing when I see you guys is I'm like mine looks like caveman dribble, and then you guys have these really clever little ways of doing things. I'm like, oh man, it's kind of cool.
Hey, I'm jump starting the car across the starter with a screwdriver. It
Hoping for
works,
the
but it's
best.
not practical.
Good stuff, man. It's awesome. I love seeing it. Thank you, Nick, for that demonstration. Let's see. Where are we at? Let me share my code, or not my code, the window specifically. right, so we did the sliding window. A not so great solution. Uh, you guys understand why or how the window works now. What here makes this a not so great solution?
The
You don't have to know how
nested
it
for
works.
loops.
Yeah, the nested for loops, right? It really all these algorithms that we're covering is just it's a way to improve your time complexity. Um, because if you were to go back to your code when you guys first started coding, whether it's the coder by challenge or any other problem, your code probably looks something very similar to this, right? Using nested for loops and brute forcing most of it. And I told you guys initially, especially if you guys came through that application or intro coding, you don't have to worry about time complexity right now. The important part is just get some code on your screen and make sure it works, right? But as you guys progress through the immersive program, you're going to start looking at your code, or you have to kind of start looking at your code in a different light. Like, is this good code? Am I writing something that's efficient? Would I be proud to submit this at work, and have it reviewed by my senior software engineer? You know, am I writing code that's going to be as efficient as possible? And is it readable? So really that's what we're trying to make sure that you guys really understand here. And here is a much better solution. Really, the sliding window just gives you a different way of managing your problem and coming to the same outcome, but with a much better way than you did before, right? So this looks fairly similar to kind of what you guys did, but a little bit more, right? We have a max sum and a temporary sum. We want to make sure that num is not greater than the length of the list. So Nick, good job on that, right? You want to make sure that before we even start iterating this, the sublist that they're asking of us, like, is it even viable with the list that's being passed in within this function? If not, then we need to be able to handle that. Afterwards, we start a for I in range to iterate through the entire, not the entire list. We iterate through the range of how many numbers do they want, right? If it's 4 numbers, then we need to iterate in range of that to get the max sum. So really, you can do it this way, or you can use the max method to get this outcome, um, to figure out what the max sum of your list is. Either or, they end up being the same time complexity. Just make sure you don't do this within a nested for loop. But notice that they iterate through. If num is 4, that means we have to add 4 different items to our max sum, which is going to iterate through the window, right? Grabbing the first num amount of elements that we have there. And then notice that they save it in a temporary variable. That way they don't lose the max sum, but they're also able to have a variable that they can work with. And then as they check the rest of the list, they're shifting their window, and then grabbing the max sum of what the temporary sum is and what the new max sum is and reassign it to max sum. It looks a little complex. Honestly, I like Nick's method a little bit better than this one. So that kind of brings up the question. So which one's better, right? Both of them reach the same solution. They both have similar time complexity, but now it comes down to which one is more readable, right? Which one's easier to understand if you were to hand it over to another developer? Like, can they pick this up and understand what the function is doing with what you wrote, right? So it kind of goes back to that slide that we have where we talked about what's better. Is it the time complexity? Is it the space complexity? Is it the amount of lines? Or is it, how neat your code is that makes it good? We start with a certain baseline, which is the same, which is the most efficient one. If both Kevin's and this method are just as efficient, well, then we go into memory, which is use the most memory. And then if they're both using the same amount of memory, then it comes down to which is more readable, right? And that's really how we're going to come out to a conclusion to figure out which one's going to be the best solution out of everybody's. This one we're talking about it, but we don't actually do anything to cover it. But the divide and conquer method, it's really it's kind of like it's binary search essentially, right? Which we're going to talk about in our next class, which we were about to start right now. But I don't know why we have this slide here. Well, essentially, it's kind of give you a sneak peek to the divide and conquer method. And this goes back to the example that Daniel used of using logarithms, right? Getting a book and trying to find a specific page, kind of open it up halfway, you check the page number, and compare it to what page number you're on, and so on and so forth. Or going back to the splitting of that list, if you guys recall the example I gave you guys yesterday. So that's really what the slide is showing you here. It's showing you how you're able to break things into smaller pieces and handle them individually. But that's going to conclude the big O notation and common problem solving patterns. We're going to go ahead and kick it up a notch, and we're going to move on to lesson 12, which is going to be searching, sorting, and recursion. And these are another set of algorithms that you're going to encounter and really that you can use. So we'll just jump straight into it. Did we take a break already for our second break? We did, right? No? I don't know if I gave you guys a break. I think we did.
I don't think so. I think it was just a one.
Okay. All right. Let's take our last 10-minute break of the night. It's 7:50. Let's come back at 8. And then we're going to start lesson 12. And it's going to start off with linear search, as you see here. We'll get about halfway through it probably before we call the night. I'll see you guys in a bit. All right. Let's go ahead and come back. Why is my keyboard turned off? Okay, so we're about to start searching, sorting, and recursion. It's gonna be the last thing that we're gonna cover today, um, and really the last actual lesson for data algorithms and structures. Tomorrow we'll start regex ASCII, and we'll probably finish this tomorrow, and then we'll start regex and ASCII characters. So searching a list, right? So searching a list for a particular item is a very common computational task. You've essentially been doing it this entire time, right? For I in nums, for I in range of nums or the length of nums, right? We have been searching through everything, right? The search is the simplest approach to searching list is for an item is called a linear search, right? Linear because we, unlike dictionaries that we can use keys to find something specifically, uh, we have to go through every individual item in a list, which is why typically for loops, depending on the conditions, for the most part, 9 times out of 10, it's gonna be for big old N, right? Linear search because we have to go in a line from start to finish, one item at a time, right? Think back to the explanation that I gave you guys yesterday of, trying to find somebody's house in a long street. You don't know the actual house number, so you go house by house until you find, I believe we use Kevin as an example. So linear search is going to be O of N, right? Because we have to go one item at a time, right? This is your typical linear search. They just put it in a fancy function here. We have two arguments, a list and a target. Target is the item that we're looking for in the list. They iterate through the list using the range and then grabbing the length of the list. And they're checking if the target is equal to list index of I, right? This is just a more complicated way of saying for num and nums or for num and a list, right? They're using the index to specifically grab an item at each index, right? This is nothing new to you guys. We've been using this. Once again, reiterating index methods and the in operator that's used on lists are both linear searches under the hood in Python. So it's not just magic. There's not a magic wizard inside your computer that's running this. It's an actual for loop, right? So having membership checks or using methods like .index, it's going to require linear searches. Binary search is going to be a more efficient algorithm for searching a list, but only if it's sorted. And that's really the keyword here, if it's sorted, right? Binary search is part of the divide and conquer pattern that we discussed last class, which is really just that last slide. And then that quick little demo that Daniel and I went through. This type of algorithm focuses on dividing a data set into smaller chunks and then repeating a process with a subset of data. So just You're dividing it and tackling one part of the structure at a time, as long as it meets a certain condition. Right? This can tremendously decrease your time complexity, typically dropping it from O of n to O log of n. Right? If you recall that graph that we had last week, not last week, I believe it was Tuesday, when we started this, uh, yesterday really, we saw that O log of n was between O of 1 and O of n. Really, O log of n really shines with the much greater that your values are. So if you're searching through a list, the bigger the list is, the more efficient the algorithm actually is. This function is going to typically accept a sorted list and a value, right? And we create a left pointer at the start of the list and a right pointer at the end of the list. So here we're already showing as a student practice. And really what the slide is trying to show you is essentially this, right? We had this list right here. You essentially, what you do is you create two pointers. We'll say pointer 1 is equal to 0. Pointer 2 is equal to length of list minus 1. All right. And we have these lists. Actually, it's probably not a good way of explaining this. You're gonna have a starts and they're not necessarily gonna be here, but you're also gonna have a third pointer, which is probably gonna be the middle pointer. Middle is equal to the length of the list divided by 2. So let's say this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You're going to divide this by 2. It's going to give you 5. So 0, 1, 2, 3, 4, 5. This is going to end up being at 6, right? So the way that this is really going to work is you're going to have a pointer pointed at the middle. And you're going to split the list in half, right? You're going to have some kind of target value. Let's say we're looking for 9 like we did yesterday. You have this target value that you're looking for. You're going to split this in half. You'll have your middle, and you're going to essentially, I don't think we need these, if I'm being honest with you. You're going to check if your target that you're looking for is greater or equal to whatever is in the middle, right? And like I said, this really works. This only works if it's sorted. This wouldn't make sense if this was out of order, because 9 could essentially be anywhere. But because this is sorted, I know that if my target is greater than my middle, then my answer really, it has to be over here, right? So you essentially have your target, you have your middle pointer. You're going to compare your target to what the item at, let's say, list at index middle, right? You're going to check, is my target greater or less than or equal to one or the other, right? Than what is at list of index middle, which is going to return 6. So obviously, what's going to happen is that it's going to come back that it's greater. So you are essentially going to delete everything from here. Is going to be absolutely useless, but you're going to want everything from the right. So now you're going to grab this new sublist here from 6 to 9, right? So you're going to grab the start of this one, which is going to be middle, to the end of list, and you're going to grab a new middle section. So this will probably end up taking the spot of either 8. Yeah, it's going to be 8 here, really. And then you'll compare your target to whatever 8 is. Is target greater than middle, which will be 8, which is going to be true. So then you will remove everything from 8 to the left, and eventually you end up here. Your middle will only be one or the other, because you only have two items, so you will end up really just split it apart, and then you're going to compare your middle to either 9 or 10, and it's going to equal one of these, right? So you cut this down instead of 9 iterations, you do this in 3 iterations, right? So this is what we were talking about yesterday. I don't. You might not really need the start pointers. Really, what you really care about is this middle pointer, being able to identify where the middle of the list is, so you can compare your target. Right, so you're going to create a pointer in the middle. Yeah, I was correct. If you find the value that you want, you're going to return the index. If the value is too small, you're going to move the left pointer up. If the value is too large, move the right pointer down. So we'll see some pseudocode in a little bit. Here's our binary search. Let's look at it real quick. Let's say 13 binary search. All right. Write a function called binary search, which accepts a sorted list and a value. Right. So here is my sorted list. It goes from 5 through 99, and the value that I'm being passed in is going to be 10. So I have to figure out, return the index at which the value exists. So wherever 10 is located at, I have to return the value. So here is 10. It is at index 2, but I don't necessarily know that. So let's do some pseudocode here. Well, these are reading, so it doesn't really matter. Essentially, I'm going to want to create let's do a line here, one. Figure out the middle of my list. And how are we going to calculate the middle of the list?
Middle of the list is going to be equal to the length divided by 2.
Yeah, so we're going to grab the length and we're going to divide it by 2. Right now, it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So 20. So this will probably divide evenly. 2, 4, 6, 8, 10. If I get the length of this, which would be 20 divided by 10, it won't actually grab this one. If I use the middle of the list as 10, it's probably going to grab this 40 as index, right? Because of the offsets. But we're going to grab divide length of list by 2 and assign it to a variable. And then we are going to compare our value to the value at index list middle, something like this, right? If value is greater than middle, then we need to do something new. We need to shift our focus. We no longer care about everything to the left of 40. We only want what 40 and 99 is. So I might do something like start is equal to list at index middle, right? Our new start point is going to be here at 40. Our endpoint will essentially be length of list minus 1. So our new middle is going to be from list at index starts, right? So whatever 40 is. And then to the end of this list, and we divide this by 2. So how do we do that? Middle will end up being some kind of value as it is. And we'll know the value because we set it to a variable. So really, we can use that variable to figure out where the middle point of this is. So let's say if middle is 10 and the end of list is 20, We will grab that 10 divided by 2 and then add it to our middle, and it'll give us probably like 86, right? Or like 15 or 16, right? So we're going to reassign whatever middle is. After we notice that we change the start of our pointer first, right? Because we're about to shift the middle. We don't want to lose where our middle is. So we want to ensure that we save the new start point to wherever middle is. Because everything to the left of middle is no longer needed. So now our most left limit is going to be what middle used to be. Our right limit stays the same. We didn't have to do anything. But we're going to grab our endpoint, subtract the starts, and then probably divide that by 2, and that'll give us to where we want to be at, somewhere around those lines. I don't know if my math's correct. I'm just doing it in my head. Essentially, you want to figure out the midpoint between 40 and 99, which will end up giving you more than likely 86 or 84. So middle will end up be a new value. It'll probably be, how do we do this? N,
You just add them both together and divide by 2.
quick maths. N plus starts, which will give me 30 divided by 2 will end up giving you 15, which will be the new middle, right? So uh, thank you for that help, Daniel. All right, so we're able to calculate the middle using some math. I'm a little dumb, so it took me a little bit longer to do this math. But we want to get a new value for middle, which was now going to depict 86, right? And then we're going to check again. After we figure out the new middle, we're going to compare our values to the value of index at list middle, which will be 15, and so on and so forth, right? Obviously, we did this wrong because 10 is supposed to be on the left side. So realistically, what should have happened is we shouldn't have switched start. We should have switched end. Start should have stayed at 0, and end should have been list at index of middle, right? Because if we're looking for the 10, we don't care for anything to the right of middle. So really what we wanted actually was this right here. So we should have switched end. And that should actually still be the same. It's actually easier because if we're shifting to the left side, it's, the starts and the end added together, it's just going to equal to the end. Divided by 2 will give you more than likely probably 18, right? This will probably give you 18. So that would be your new middle. This will end up being like 18. And you're going to compare, is my target less than or greater than 18, which is going to be less than. So we're going to switch our end once again. Our end will now be whatever list that index middle is. And we just repeat this process as we slowly start to decrease the variable that we're working with, right? This list, we are eliminating half every single time as we go through this process, eventually reaching the 10, right? Does this make sense so far? But essentially, you're going to require some kind of pointer to tell you where the middle is, where your start, and I guess you are going to need your start and your end pointer now that we start writing some pseudocode. I can see that. Let's give it a try. Time is 8:17. This one might take a little bit longer for some of you guys if you've never done it. So let's go into 8:40. At 8:40, we'll come back. We'll take a volunteer if you guys are done. If not, we'll walk through it. And then I want to give you guys a resource to practice your data structures once we're done with the class. So give it a try. I'll see you guys in a bit.
So basically what I did is I set a counter to 0 because I know that if I can't find the number in there, I needed to end the test case at some point. So then I took the middle to first get my first pointer. And then I set while counter is less than or equal to the length of the list divided by 2, because if you take a length of the list and you're cutting it in half over and over and over again, the most amount of times you can cut it half is the initial value of that list divided by 2. and then we pass in our target. So if target is greater than our list middle, then we're going to basically just scoot to the right side of that list, basically by using making an end pointer, a start pointer, and finding a new middle. And then I just incremented the counter just plus equals 1. So that way I know that I've gone through that list one time, that search function one time. Similar with the minus side, right? So if I'm looking at the left side, same scenario. And then if I found it, then I just returned what the middle was. And then if I ran through all my test cases but didn't find it, then I returned a -1. And no. And then there you go. You can see there I was printing out the middles before, but what the middles were. Let me clear my terminal so that way you guys can see it. There you go. So 2, 16, and then -1.
Awesome. Good stuff. I'm going to hit stop sharing your screen, Daniel. That's exactly what I was looking for. And to be fair, for those of you who might have struggled a little bit, what I should have done is I should have shown you the next slide, which I failed to do, which is a binary search example, right? So this is fairly similar to what Daniel did. Uh, Daniel used a counter where the example here, which I would have recommended, was to use the first and last here, because as you are dividing your essentially your list right in half and shifting your sub list into a much smaller group that you're working with. Your first and your last are coming together. At some point, you're going to reach two individual values, and you won't be able to divide any further. So at that point, once you start reassigning first and last, and they're equal or greater to each other, in a sort in a sense, then you have nothing else to continue dividing amongst, right? Well, while counter was a very good way to go about it too, this is another approach that you guys could take as well. Both of them work the same, but essentially this kind of shows you here the start and the endpoints, and then while the start and the endpoint do not meet, right? That means we still have values between the start and end that we have to check between, right? And then we're just dividing it, and as we divide, if our target is greater or less than the middle, then we're just bringing our start endpoint closer to each other and just chunking away through our list until we find the value we're looking for. If at some point we only get two values left over and our value isn't equal to either one of them, then we can't shift our we can't split it in half any further. Our first and last are going to equal to each other. Um, so then at that point, we would return -1, right? Of the same concept here, right? We're just breaking apart into smaller chunks, comparing the values that we're working on to see if they match our target or somewhere around the range of the target, and then shifting to the left or to the right, depending on whether it was greater or less than. And that is your binary search example in a nutshell, right? We're gonna go ahead and stop here for this lesson. The next thing that I want to cover, let me go ahead and stop sharing my screen, see if I can pull this folder up to show you guys what I'm going to share with you guys. I like to share books. I know books is not everyone's favorite. They don't like reading it. If there's any book that I would highly recommend for anybody, if you didn't review the Python crash course like I gave you guys, the only book that you would ever need for data structures is going to be this book here. And it's going to be Groking's algorithm. I'm gonna give you guys this PDF version of it. It's very zoomed in. But Groking's algorithm is probably the best algorithm book I've ever came in contact with. I'm gonna give you guys a free copy. I'm gonna drop it in the FOP channel. This book breaks it down in such a dumb and simple way that I cannot exaggerate how easy it is to understand some of these concepts from the divide and conquer method to more complex algorithms like recursion. It breaks it down in a way that anybody could understand. I can give this to my 3 year old. A little bit of an exaggeration, but anyone can really understand it. It has good pictures. Really, it's very childish to say that, but uh, it looks like there's a lot of words here. But really, once you actually get into it, it's very simple. The way they explain stuff, and they'll show you kind of like little pictures to depict what the subjects are trying to show you and how it works. Um, and they'll even give you, I believe they give you some code snippets too, right? So they'll show you how it works in code. This one right here that they're talking about is logs, right? So they'll show you logarithms. Um, I remember seeing something like here's binary search. So here they'll show you how binary search works with some simple pictures. They break down every single point of your code. Look at this, like very, you know, very easy to follow along with. They'll show you what each part of the code is supposed to mean. Um, Let me show you the divide and conquer method. Where's it at? They talk to you about how memory works, arrays, linked lists. So if you want to work with those, they'll break it down into easy ways to understand. Here's recursion. They'll break down recursion as well. Uh, so I know initially it seemed a lot like a lot of words, but once you guys start reading into it, you'll realize how simple it is. And they're very cartoonish drawings, right? They look like sketches, but it really just adds to the charm of this book. They do a great way of explaining. Like, here's a divide and conquer method. They show you uh, like a piece of farmland, how they break it off into pieces and chunks, and how they work with the different parts. How the same strategy that I was trying to show you guys with code, they break it down with like pictures. So it's really cool, very easy to read. When it comes to books, guys, learning with books, the best approach really is um, you don't have to tackle this entire book in a day, right? That's not really what you want to do because realistically, you're not going to soak in all the information. I would go here and just start with the first chapter, right? In a first, in a day before you go to bed, or maybe when you start your day, your coffee in the morning, open up this book and tackle something new, like introduction to algorithms, right? So you'll talk about binary search. They'll break down big old notation in a much more simpler way as well. If the way that I explained it wasn't a way that resonated with you guys, hopefully this book can help you as well. And then every single day, just make your goal. Like I'm going to tackle a new chapter, and the chapters really they're only like 15 uh, pages long. It's nothing heavy right here. Recursion 38 to 50. That's 12 pages of learn recursion. Not nothing too heavy. Um, Quicksort is a very helpful one. Hash tables is a very powerful thing to learn. Uh, Dynamic programming here it gets very complex stuff. If you want to learn more about dynamic programming, you can tackle it. But really, where you're gonna get the most bang for your buck is from chapter 1 to really chapter 5. Like you can tackle this in a week. Um, and it'll give you a general understanding of some of this stuff. And they'll even give you the answers to the exercises at the very end of this. So grokking the algorithms. I give it to every single class that comes through. I was given this book by another student when I was coming to the program. We actually had like a huge repository where we dropped all like our links, cheat sheets, references, and books. We had like 20 books in total that people were just dropping. Like everyone had bought in their own books and version stuff, and we kind of accumulated them together and we shared amongst each other. This is one of the things that stuck with me, which is Grokky's algorithm. Everyone I share this with, they love it. Um, so if you feel like you struggle with these concepts, you feel like they're difficult, because really, like you know, plain and simple algorithms and data, it's not sexy at all, right? I would think it's boring, right? It's not really what you expect it to be doing as a developer, right? You want to make websites and make applications, but we can't get over the fact that the first hurdle, the first gate into getting a job is going to be that technical interview. So understanding data structures and data algorithms and how to tackle these it's going to go a long way. Um, the program has been revamped to a way that you're doing data structures every day at the end of the day. Typically, what we do is between the hours of like 4 and 4:30, or I believe it's like 4:30 to 5, we'll do a daily algorithm. So we'll come in together. You guys will get 10 minutes to try out, or I think it's like 15 minutes to try an algorithm. And then no, it's 5 minutes where the instructor will write some pseudocode about the problem that is being given to you guys. They try it out for about 10, 15 minutes. And then the other 10 to 15 minutes, depending on how difficult the problem is the instructor coding it out. So you will get constant practice with data structures and algorithms. So we realized that, students were coming through, we were focusing on nothing but full stack development. And then we were sending you guys out into the real world. And now you're like, oh, shoot, I haven't practiced lit code in months. Like I'm struggling. Like I don't even know how to approach this problem. So we now make sure that by the time you guys are reaching graduation, you have a general understanding and you feel fairly comfortable being presented with data structures and algorithms. And grokking the algorithms here is a really good way to kind of jumpstart your journey to working with data. So definitely check out grokking algorithms. Take it one chapter at a time, right? It's as simple as read it as you drink your morning coffee to kind of start up before every day of class, right? Uh, you guys have like was it 18 weeks? I think it's 18 weeks. I don't remember what the length of the program, like 18 weeks that you guys are gonna be with us. So uh I would make it like a habit. Who here has like habit trackers? Anybody have like habit tracker apps? You guys like self-improvement stuff like that? Anybody? All right. Uh it's good and helpful to ensure that you instill healthy habits, especially when it comes to software development. Software development is an industry that is constantly growing, right? We have new frameworks, new technologies. Nowadays, we have AI, stuff is shifting to AI. Um, you guys are gonna have to learn AI as well if you want to have a job in this industry. Really, that's where the world is going. AI isn't replacing developers, but it's being used as a tool in the industry to increase productivity, right? So if you want to make sure that you are keeping up the times, you're gonna have to get good with AI. You're gonna have to learn new frameworks. You're gonna have to learn new languages. I'm telling you right now, when you guys get your first role, chances are it's probably not gonna be in the language that you guys learned. Uh, you might have to pick up Ruby. Some of you guys might have to pick up Java. Uh, you know, uh, Different languages depending on uh, the company that you're working with. So this industry is an industry that you're constantly having to learn. So make sure you guys are instilling good habits early on, and it starts here. Something as simple as reading a new chapter, something new every single day, like the Grokking algorithms. So I'm gonna go ahead and drop this book in the chat, um, and we're gonna end this class with this note. Thank you guys for showing up today. I will see you guys tomorrow. We have 2 days left before the end of Foundation Programming, and then you guys start your immersive program. How exciting! Let's go ahead and stop the recording now.